Again, picking up where we left off, we are looking at the elements of quantification that allow us to represent the traditional four types of categorical logic, A, E, I, and O. So we've covered A, and we derived this expression, which we can read as for any x. Remember that this upside down A stands for the universal quantifier. So for any x, if x is S, then x is P, which in other words means all S's are P's, right? Now what would we say about E? We want it to mean no S is P, and so it's obviously a universal proposition. So following on this model here, we could guess that it's going to be for any x. If x is S, then what? Then x is not P. That accords with common sense, but it also makes sense when we think about the diagram for this proposition. So think about it. If anything is an x, in other words, if anything is in this region, then it's outside the P region. It's not a P, right? So this is the places where things that are P would live. And so if anything is an X, then it's not a P. Now you might be thinking to yourself, okay, but what about things that are P's not being S? I mean, that's also a part of that claim. And sure enough, it is. And all you have to do to derive that is remember the one of our axioms, transportation. So how does transportation look? It's P implies Q is logically equivalent to not Q implies not Q implies not P. Now, if you think about transportation applied to this expression, how is it going to work? It's going to work like this. The S of X implies not P. Transported is going to be not P. And over here we've got not S, and you keep the implication sign, just as in the schema for transportation. Then we apply double negation to derive P of X implies it's not the case that S of X. So what we find is that this expression, with its quantifier out in front of it, these two expressions are logically equivalent by the axiom transportation, right? So all is well in terms of the meaning that we want no S is P to have. It's all turned out to be logically equivalent to what we think no S is P means. So looking at this expression one more time, what do we have? We have for any x, if x is S, then x is not P. And by transportation, we can say the flip of that. For any x, if x is P, then x is not S. Okay, great. That's our two universal types of propositions. What do we do about the existential types? So obviously these, let's go back to our some S is P is the traditional formulation of an I. So now we can begin down this road by noticing the same thing. We'll treat S as a predicate with an argument X, and we'll treat P as a predicate with an argument X. Now let's reflect for a moment on what some S is P is actually claiming. It's claiming that there is at least one thing that is both S and P. So notice, it's not claiming anything sort of conditional, like if something is an S, then it's a something else. It's not claiming that. It's actually claiming that there's a thing, that X right there is a thing, and it is both in the S circle and also in the P circle. So the major operator that we're going to work with here, instead of being implication, is and. Remember, I just said the word both. So both and. It's both S and P. So now we've got the basic idea. We need to do something to indicate that we have an existential proposition, a particular, instead of a universal. So We have another quantifier for that. It's a backward E. So we have an upside down A and a backward E for the particular, which in this logic we call the existential quantifier. The existential quantifier is what we use for particular propositions, and that's what we call them in categorical logic. So what we're going to write here is the existential quantifier applies to X, and how do we read it? It means there's at least one X. There is at least one X such that X is S and X is P. That is exactly the meaning of this and this. So the backward E you can read it as there is at least one, or some people read it as some X. That's a little more in keeping with this, but I like there's at least one X such that, and then we have the rest of our expression. To me, that captures the meaning a little bit more clearly. And if you get in a habit of that, then when you see the existential quantifier, your brain will automatically snap to that, right? So now let's formalize O. We know that it stands for some S is not P in categorical logic. So let's fill in all of our elements. We're going to treat S like a predicate. We'll have S of X. We're going to treat P like a predicate, so we're going to have P of X. Now, we've got an AND here, but what does this proposition actually claim? It's claiming that there's at least one thing that is an X, so it is one of these, and not a P, not one of these, so and not P. So we have the basic meaning and syntax of this expression. All we need to do is fill in the existential quantifier to tell us what goes in for the X. So it tells us that there's at least one X, there's at least one thing X, there's at least one X such that X is an S, but not P. And that is exactly the meaning of this diagram and also this categorical proposition. So now we've got all of our categorical propositions mapped out in terms of the symbolism using these elements. We have subjects and predicates. We have quantifiers that correspond to universal and particular. The universal quantifier we just call universal quantifier, and we read it for any X. The existential quantifier corresponds to particulars, and we read it, there's at least one X. And now we have the basic form for all of our categorical propositions. So let's look at those more isolated so that it's clear what we have going on here. So here is our square of opposition. So we have A, E, I, and O. For A, we're going to write for any X, S of X implies P of X. For E, we're going to write for any X, S of X implies not P of X. For I, we're going to write there's at least one X such that X is an S and X is a P. And for O, we're going to write there's at least one X such that X is an S and not a P. All right, so now, using these as our basic types, let's formalize a proposition just to illustrate how this works. Let's formalize some snakes are not good pets. So, let's start with the categorical version of it. Some snakes is not, let's use G to stand for a good pet. Would have been prettier to use P because then we would have had parallelism, but that's okay. So this is our proposition in a categorical logic sort of schema format. So that's fine, but now how do we apply quantification theory and its elements to that? Well, we'll convert this to a predicate and this to a predicate. And we'll use our model here. This model tells us basically the form. So within the expression, the syntax is going to be and not, and then the quantifier is going to look like this. So what is this? How would we read this? We would read this like this. There's at least one X such that X is a snake, but not a good pet. And that's exactly the meaning of the original categorical proposition, some X is not G. All right, one more example. How about no cows are mammals? Categorical version of that is no C is R. And following our pattern for the universal negative, we will be able to write this as C of X implies it's not the case that R of X, and we use a universal quantifier in front. So now how do we read this? For any X, if X is a cow, then X is not a reptile. All right, now why do you think it is that the universal propositions both need the material implication, whereas the existential propositions both need an and as the major operator inside the scope of the quantifier? Think about that, and in our next tutorial, I'll explain why that is and why it's so important that we get this straight. And I'll give you a hint as you're thinking about it. It has to do with the distinction between the Aristotelian interpretation and the Boolean interpretation. Yes, you probably thought it was too good to be true that we left that in the past, but it keeps cropping up because whether something exists or not makes a difference in terms of what we can claim about things and their properties.